Welcome to TechDaily.AI, your source for technical information. This podcast is sponsored by StoneFly, your trusted solution provider and advisor in enterprise storage, backup, and disaster recovery, hyperconverged VMware, Hyper-V Proxmox cluster, AI servers, and public and private cloud. Check out StoneFly.com or email your project requirements to sales@stonefly.com for more information. Okay, let's unpack this. Ever wonder why your super fast computer sometimes feels like it's, I don't know, wading through molasses when you're just saving a file? Or maybe opening an app?
Yeah, it's a common frustration, right?
Totally. So today we're going to dive into why some of these seemingly simple computer operations can take a surprisingly long time. We'll be exploring the crucial role of input-output, I/O operations in creating these digital bottlenecks.
And it's fascinating, isn't it, how the parts of a program that often feel the slowest involve this interaction with the outside world relative to the processor itself.
Like saving a document.
Exactly. Or retrieving information from a database somewhere, maybe on a disk drive. Even just the delay while a program waits for you to click a button or type something in.
Right.
These are all examples of I/O, and they can introduce some really significant slowdowns.
Exactly. You'd think with the incredible processing power we have now, everything would just happen instantly. But here's where it gets really interesting. There's this massive speed gap inside your computer.
Huge gap.
Accessing RAM, that's your system's super quick working memory that happens in nanoseconds, like practically instantaneous.
Blink and you miss it. Almost.
But then, when a program needs to read or write data to a disk drive, or maybe talk across a network, suddenly we're talking about milliseconds.
Milliseconds, and that doesn't sound like much, but compared to nanoseconds.
It's a different universe. We're talking millions of times slower. It's
Okay.
huge.
It really is. And that massive difference is why optimizing how and when our programs talk to these slower parts is so critical for making software feel responsive.
Yeah, it's like, imagine trying to fill a swimming pool with a teaspoon versus a fire hose. That's kind of the scale we're dealing with here.
Good analogy. And let's not forget bandwidth either, connecting to the bigger picture.
Right, the transfer rate.
Yeah. Your RAM can shuttle gigabytes of data every single second. Massive amounts. Now, compare that to, say, a traditional hard drive or even many network connections.
You're often looking at megabytes per second, right? Maybe low gigabytes if you're lucky.
Exactly. So even if the initial delay, the latency wasn't an issue, just the sheer volume of data needing to move can create its own kind of traffic jam. Another bottleneck.
And okay, you mentioned it earlier, but let's not overlook the human element here.
Mm-hmm.
Sometimes the biggest I/O wait is just us.
Mm-hmm. Waiting for user input.
Yeah, waiting for me to type something or click OK.
Yeah.
And that's not just slow, it's completely unpredictable. You never know when that click is coming.
Which makes programming for it tricky. So this raises a key question. What's actually happening inside the computer when it hits one of these slow I/O tasks?
Like fetching data from a disk.
Yeah, let's use that example.
All
So the part of the program doing that works, let's call it a thread. It can become blocked.
Blocked, okay.
Imagine like a traffic light system. Green means the CPU is busy, working away. Red means the thread is blocked, waiting.
So while that light is red,
The CPU might actually be sitting idle, essentially twiddling its thumbs, waiting for the slower disk to cough up the data. This could be for an API call, one program asking another for something, or maybe a database query, or just writing data out.
okay, so the immediate sort of logical thought might be, well, hang on. If one thread gets blocked, why not just throw more threads at it? Surely more workers will solve the problem.
It seems logical, definitely. That's often the first instinct.
Yeah.
But it comes with its own set of problems.
Right. It's not a free lunch.
Not at all. While having multiple threads can let a program juggle several tasks seemingly at once, each thread needs resources. It needs memory. It needs some CPU attention.
Even if it's just sitting there waiting.
Especially then. If these threads are mostly idle, just waiting for I/O to complete, they're basically occupying valuable system resources without doing active work. It's like hiring a bunch of extra construction workers, but they all just stand around waiting for a truckload of bricks to arrive.
They're on the payroll, using up space, but not actually building anything.
Precisely. So just throwing more threads, more raw processing power at an I/O bottleneck isn't always the smartest move. It can actually make things worse sometimes.
How so?
Well, Managing lots of threads gets complicated. You run into potential issues like race conditions.
Where the order things happen in matters and it can go wrong.
Exactly. If two threads try to update the same piece of data at the same time, the result can be unpredictable, maybe just wrong. Then you have things like deadlocks.
Where everyone's waiting for everyone else.
Yeah. Kind of, yeah. Threads get stuck waiting for resources held by other threads, which are waiting for the first ones. Gridlock. And similar issues like live locks. Plus, just the act of the operating system constantly switching between all these threads, that's called context switching, takes up CPU time itself. It's overhead.
Okay. So multithreading has its place, obviously, but it's not the silver bullet for these I/O problems.
Not necessarily, no. Especially not for heavily I/O-bound tasks.
All right, so if just adding more threads isn't the answer, what are some of these more efficient techniques you mentioned? Tell us about this. Event demultiplexer. Sounds pretty technical.
It sounds technical, but the core idea is actually quite elegant. It's based on a technique called multiplexing.
Multiplexing, like combining signals.
Essentially, yeah. Combining multiple signals or inputs to share a limited resource more efficiently. Think way back to old-school telephone switchboards.
Okay, with the operators plugging cables in.
Exactly. The operator didn't constantly monitor every single phone line. They waited. When a call came in, a light would flash or a buzzer would sound, an event happened. Then the operator connected the call. The switchboard wasn't actively polling every line. It was waiting for signals that work needed to be done.
Ah, I see. So the event demultiplexer is like the operator. It waits for a signal.
And precisely. Instead of having lots of threads constantly asking, is my file ready yet? Is my network connection ready yet? The system uses this demultiplexer to wait for notifications from the I/O sources themselves.
So the system gets told when something actually happens, rather than having to keep checking.
That's the core idea. In a computer, these phone lines or event sources are things like file descriptors handles to open files or network sockets, which are the endpoints for network communication. Timers can be event sources too.
And what kinds of events trigger these notifications?
Things like data is available to be read from this file, or this network socket is now ready for you to write data to it, or maybe a new incoming network connection request has arrived.
Okay, that makes sense. And I gather modern operating systems have built-in support for this kind of model.
Absolutely. It's fundamental to how they handle I/O efficiently. Linux has mechanisms like epoll, which built on earlier things like select and poll. Sometimes you hear EOL mentioned in that historical context. Mac OS uses queue. Windows has its I/O completion ports, or IOCP.
IOCP.
All of these are basically sophisticated ways for the OS to tell an application, hey, something happened with one of the I/O operations you were interested in.
Now, this whole approach,
Mm-hmm.
it sounds very much like how some modern programming environments work under the hood, like
Yeah.
Node.js comes to mind.
Exactly. Node.js is a prime example. It makes heavy use of this event demultiplexer concept. It does this through a library called Labouv.
Okay.
That library is the engine that lets Node.js handle a huge number of concurrent I/O operations, network requests, file operations, timers, background tasks without getting blocked. It uses an event loop, powered by Labouv, to listen for these I/O events from the operating system.
So instead of one thread per connection,
Yeah.
maybe?
Right. It manages many connections with fewer threads. When an I/O operation finishes, Labouv gets notified, puts a callback into a queue, and the Node.js event loop picks it up and runs the JavaScript code associated with it. It's generally much more resource efficient for I/O-heavy applications compared to the traditional one thread per task model.
That makes a lot of sense. All this talk about handling I/O efficiently, especially with large amounts of data and needing responsive systems, it really brings to mind companies that specialize in this, like our sponsor, StoneFly.
Absolutely. StoneFly operates right in that space. They're leaders in providing high-performance, efficient data management solutions. Think enterprise storage, backup, disaster recovery, areas where minimizing I/O bottlenecks is just critical for performance and, frankly, reliability.
And they've got some pretty advanced tech behind their solutions, right?
They really do. StoneFly offers a suite of advanced data services, things like immutable snapshots, crucial for data protection, especially against ransomware.
Immutable meaning it can't be changed.
Exactly. They also have strong AES 256-bit encryption, both for data sitting on the drives, at rest, and when it's moving, in transit. Security is key.
Makes sense. What else?
Well, there's synchronous and asynchronous replication for high availability and disaster recovery. intelligent tiering, which automatically moves data between faster and slower storage to optimize costs and performance, smart flash caching to speed things up.
Okay, that's quite a list.
And there's more. They have specific ransomware protection features built into their storage volumes. Plus, they've actually patented their approach to immutable and air-gapped repositories and control nodes.
Air-gapped, so physically or logically isolated?
Typically logically isolated, creating a gap that malware struggles to cross. They also offer campus mirroring for redundancy across sites. And the impressive part is managing all this potentially from one node up to 128 nodes across different locations through a single user interface.
Wow, a single pane of glass for potentially huge infrastructures. That's important.
Definitely. It simplifies management. StoneFly's whole goal is to help organizations protect their data, expand storage easily, boost performance and scale, or maybe just refresh their existing infrastructure.
Whether that's storage, backup, DR, hyperconverged systems.
Right, or server infrastructure running VMware, Hyper-V, Proxmox. They cover a lot of ground, and they emphasize doing it at affordable prices with solid support.
It's also worth noting StoneFly's actually been recognized for this. They received a DCIG award, placing them among the top 5 storage companies across SAN, NAS, and object storage categories. That's quite an achievement.
That really speaks to the breadth and quality of their offerings.
And they're growing too. StoneFly mentioned they're a fast-growing company with over 100 job openings right now.
Oh, wow. In what areas?
Areas like software development engineers, technical support, full-stack developers, digital media experts, customer service, a range of roles. If you're interested, you can reach out to jobs@stonefly.com.
Good opportunity for folks in the field.
And they have a special offer for our listeners this month. Actually, 2 options. You can get immutable and air-gapped backup starting at just $10. Or, for larger needs, there's a 70 terabyte backup and disaster recovery appliance, which is expandable up to 4 petabytes, by the way.
70 terabytes expandable to 4 petabytes. That's serious capacity.
It is. And it includes that air-gapped and immutable support for platforms like Veeam, Rubrik, Commvault, Site Recovery. Plus, it comes with an advanced AI appliance featuring their object lockdown technology for ransomware protection. That whole package is $700.
$700 for a 70 TB appliance with all those features. That sounds like a very aggressive offer.
It really does. So to find out more about these specials or just StoneFly's full range of solutions, you should visit stonefly.com or email your project needs to sales@stonefly.com. StoneFly. Definitely worth checking out.
Okay, so wrapping things up, we've seen that I/O operations are often these hidden performance killers in software.
Yeah, the bottlenecks.
It really boils down to that fundamental speed difference between the super-fast CPU and memory and the much slower world of disks, networks, even user interaction. And we saw how managing tasks waiting on this slow I/O, especially lots of them, gets complex with traditional threading.
Right. The resource drain, the deadlocks, all that complexity.
But then we looked at smarter techniques like the event demultiplexer model.
The telephone switchboard analogy.
Exactly, which is much more efficient and scalable, and it's the kind of approach used under the hood by systems like Node.js with Lubov.
So it really shifts the focus from keep checking to let me know when it's done.
Precisely. It's a more event-driven way of handling things.
Okay, so here's a final thought for you, our listener, to mull over. Given how much modern computing relies on network requests, fetching data from databases, saving files, essentially constant I/O, how might these principles of efficient I/O handling continue to shape the future?
Yeah, think about software development, the infrastructure needed. How will optimizing I/O impact the responsiveness and, maybe more importantly, the scalability of everything we build and use online?
Interesting question. Lots to think about there. Well, thanks for taking this deep dive with us today.